It is on.
Okay, thanks. My name is Jean-Thomas Coiva. I work for Ii Ddn. So today I'm going to talk a bit about large language model, but seen from, I will say, a storage vendor perspective. I may have too many slides, so maybe I will skip some of them. For example, this one. So AI is still strong. It's not the buzzword which is going to fade away as we were thinking at some point. There is always a new AI things which trigger again a lot of momentum. So usually when we look at AI from a data standpoint, we see three big challenges. I mean, for AI applied to science. First of all, is like the amount of data that we need to manipulate is coming from various data acquisition device. It could be like microscope, it could be antenna for astronomy. So there is a lot of complexity and diversity to handle this. So I would say that the first challenge that we are thinking about. The second one is more like data is kind of transversal to the organization. So we need to process the data, to calibrate them, to curate the data, to process, to do the training, the inference, the analysis, the archiving. So there is a whole pipeline for the data and it needs to go through different layers of the organization, different silos. So this is also one technical thing that we have to address. So that was one of the classic, not classic, but let's say traditional problems that we have. And the last one is a bit more complicated, is that there is a lot of regulation or legal issue with data. You don't want to have bias, you want to be able to audit, you want to provide protection and security. So all these things has to be handled by the, let's say, the data management solution that we are building. For large language model, there is, I would say, an additional complexity which is popping up, and it was quite unexpected. So first, these things, they are complicated. So it has been mentioned yesterday, there is a lot of publication made every week on LLM for sure. Okay, that's great. But it's a lot of work. And if you look at the number of authors on this publication, this is just amazing. This is paper written by 20 people. So it's not just like a lab thing, it's like industrial process. And so this is kind of a personal point, but I think these guys, basically, they are putting a lot of effort to build this very large and complicated model, and they are building their legacy code. We have legacy code in HPC, and we know that it's difficult to maintain, it's difficult to evolve. So when a new hardware arrives, it's always a bit painful because you have to rewrite part of your application. And I think the AI people, they are at this stage now. They are building huge applications, very complicated, and they will enter into the difficulty of maintaining it and evolving it over the years. So this one is a personal opinion. So LLM on storage, it has been studied a bit. So I think this one is coming from Facebook. And they look about the energy consumed for the whole pipeline, the training. And actually, on three different workload use case that they have internally, on the average, more than 50% of the energy is consumed by the data, not the training, not the GPU itself, but just storing the data and moving the data out of the storage to the GPU. So it's a hint that somehow the data angle is quite important for this large model. And there is, of course, as always in our field, it's always a bit more complicated. You know, if you open something and you discover additional complexity, is that, okay, there is a decorrelation between the need to move more data, so the capacity, and the bandwidth. And actually, the bandwidth requirement is evolving faster than the capacity. So we have huge data set, but we need even more bandwidth by a factor of 2 in order to feed this GPU monster. So I think this is well accepted by the community, and the ML Common or MLPerf community has no special interest group dedicated on storage. So here is the link. So the key people, I mean, the key person is at McGill. Basically, this is an academic lady who is managing the group, and there is a vendor and other people working with her. And now if we look a bit more further about this LLM, so they are large by essence, but actually they are becoming larger and larger. So this is a trend about the number of parameters that this model are using. So there is a trend line over the 10 years, but if we just look at the last 3 years, basically they have augmented by 1 order of magnitude every year. So after 3 years, it's like the number of parameters has increased by 1,000. At the same time, the hardware is not able to keep pace with this. 1,000, even for us computer guys, it's a bit too much. So the GPU architects have succeeded to increase the memory of the GPU by a factor of 5, which I think it's quite an achievement, but it's by far not matching the pressure exercised on the hardware by this model. And here, this interesting, this is the A100. So the A100, I mean, it was a previous generation, the flagship generation of NVIDIA. This is the memory. So it means that this model, Bloom, GPT-4 and GPT-3, they are not fitting in the memory of the GPU. So you cannot train this model on a single GPU. So you need to find something else. So if we look at the way that the memory is consumed by this model, the number of parameters actually is just an indicator. And then after, we need to convert this in byte because we are computer people, right? And there is, roughly speaking, so of course it depends from the model, but let's say that there is a factor of 16. So there is parameters, gradients, and optimizer states. The optimizer states are additional value which are attached to each parameters, and actually they are the one who are taking the more memory space. So it means that if my model is 17 billion parameters, which is large but not huge by today's standard, I have almost 300 gigabytes of memory to fit my model in. And I do not have 300 megabytes of memory on my GPU. The largest one available, if you can get one, is the H100 from NVIDIA, and there is 80 gig. So it means that I cannot fit the model in the single GPU. So this is what they call the memory wall. And of course, furthermore, we're talking about the 17 billion, but there is already a model with 170 billion, and we can foresee that in few years from now, we'll have trillion of parameters. So we need to, there is some kind of conceptual change here. We cannot just, put more data on the GPU. It's not scaling, except if you have hundreds of GPU and then you parallelize the code. And then there is also here a little point that I would like to make. It's a bit personal, but if you need hundreds of GPU, it means that the people will be able to innovate in this domain. They only will be very large organization with a huge amount of hardware available. So in order to fit this large model in the hardware, basically there is several parallelization scheme, data parallelism, model parallelism, and pipeline parallelism. So the first one actually is data parallelism. It's just to accelerate the training. You just replicate the model in the different GPU, and you throw the data to this GPU. So you're getting a train faster, but actually it's not improving the memory. But these two second options, the model parallelism and pipeline parallelism, basically you slice the model either vertically or horizontally. And so you can fit part of the model in the memory of the different GPU. So then you can basically scale. So if I have 10 GPU, I will have 800 gigabytes of available memory if I'm running H100 from NVIDIA. There is no free lunch, right? Because it requires communication and synchronization across the GPU. So here, if we are within a GGX, which is an 8 GPU machine, we have a very good intercommunication between the GPU. But if the model is spanning several GGX, then of course the communication overhead increase and you degrade the efficiency of the thing. Yes, so for instance, in a paper from Microsoft, they show that if they span the same model across 2 GGX, the efficiency is going down to 5%. So it's not very good. Actually, this is what we are observing in our data center for HPC, but maybe AI is following the same way, right? So here, this is something that we are looking at quite, I would say, with attention at DDN. This is a zero model coming from Microsoft. So basically, they are trying to parallelize in a very subtle and sophisticated way in order to maximize the amount of data that you can dispatch across the GPU without having a too high communication overhead. So it was published in 2020, and they were very pleased with the result, and actually they are quite excellent, I would say. If you have a lot of GPU, then you can apply this, it works well. If you do not have a lot of GPU, and even if you have a lot of GPU, but the model is increasing so fast that maybe there is still an issue. So they extend their model. So it's the next year, so 2021. So they call this zero infinity. And basically, they are rediscovering the out-of-core computation, which is something that we know in HPC. If I'm not able to fit my mesh in the memory, I have part of it on the storage. And so we know to do this since decades, and we know it's complicated. And now the large language model community is basically applying the same technique. So the idea is that we are going to offload not on the memory of the other GPU, but we are going to offload in different layers of the memory hierarchy. So if we look within a DGX, there is two levels of memory. The memory, which is, I will say, private to every GPU. So in your case, 80 GB for the flagship. Then you have a second level of memory, the CPU, which is larger and shared. So we can offload part of the model, thanks to zero infinity, to this larger but further away memory. So it means that basically, if I move my part of my model here, I will have a larger model, but I will degrade a bit the performance. And there is even two layers of storage, the local storage, so very fast NVMe directly provided within the DGX. On the remote storage, there is in the DGX architecture, there is two network ports dedicated to storage. And we are basically plugging our DDN storage to this port. We did some micro benchmarking to assess what is the quality of these different layers. So of course, we are storage person, so we focus on storage. And what we do observe, we did observe, is that actually the bandwidth is much better if you go to the network attached storage. So if you have I would say, a convenient, proper parallel file system, such as a Lustre, you can have a much higher bandwidth through the network than if you go to the local storage, to the NVMe. Of course, the explanation is pretty straightforward. It's the number of PCI lane in the architecture of the system. Now, if we look at the latency, if we do a lot of small IO requests, then this is the opposite way around. The local NVMe are much better than actually the network attached storage. So it means that there is, again, a bit of complexity here. And this is one point here that I would like to make. So we did also some benchmark on, actually, it's people from McGill who did this, but I've stole the picture. They try to understand from where the latency is coming when I'm doing a ping on my NVMe drive within my system. And most of the latency is actually coming from the software. The hardware, it's here. So from the block driver to the hardware, I have like maybe 12 or 13 microseconds. But before that, I need to have the NVMe driver talking to the block device. And before that, I need to have the application talking to the NVMe driver. So it means that overall, most of the time is spent in software layer. So this is I would say, a point for us that we need to be very careful about writing good software if we want to leverage
Okay, thanks. So the metric that we are trying to push for, so it's a work in progress. We want to have the paper ready by ISC, so it's a bit of a rush. Is basically the GPU utilization. So just to try to capture how good is my offloading techniques, that I'm able to leverage to use most of my investment in terms of GPU. I'm not going to enter into all the details, but let's say that we are here, so better than the other storage, not as good as the CPU, but we are not time size constraints. So overall, for what we get at the moment, the efficiency is around 80%. So if you have no constraints on the size of the model, and you still get 80% of the GPU capabilities. So if you compare to the 5% when you do a naive parallelization across DGX, I think it's a pretty good result. So we do foresee, so maybe I'm going to skip this one, but we think that more data issues are coming actually for this very large model. They are racing at the moment for the model size, but at some point they will have to race also for the amount of data to train them. Okay. So our methodology in this, I will say, difficult AI market, because AI is difficult because it's complicated and it's moving extremely fast. It's almost impossible to keep pace with the amount of papers, innovation. It's kind of a struggle. So we don't do this by ourselves alone. So we team, and actually we try to team with the best. So notably, we have a very good relationship, industrial relationship with NVIDIA. So this is currently our largest customer. We try also to get feedback from the deployment that we have with our customer. So this is very important. So for example, Jean-Zé, this a French machine, use DDN storage, but so more importantly, I mean, it's important, of course, that they use DDN storage, but then we can discuss with them and understand, what they are doing, what are the problems that they are facing us with data management and so on. So that's quite an important source of information for us. And also we team with academic people who are writing all these papers. We are a company, so we need to deliver products. So basically we buy hardware. So we are going to get our H100 in the lab, and we sourcing at it. We try to have simple metrics so we can demonstrate the value of the product. So it means that we have engineering people not doing storage, but just doing evaluation of AI framework on the storage. And also we cannot just survive with this experimental approach. We have to invest a bit of time on engineering and kind of research to try to understand, to read the paper and to write some. And of course, we are an open source contributor. So at the end, my two marketing slides, you will not avoid them. The first thing is that software is really important. I think it's even a technical point. It's not just a marketing one. So software actually is critical. So because this is moving so fast, we need to have performance knob. We need to have a way to adapt and configure the software stack to the workload, because the workload is evolving over time. It's changing quite fast. Second thing is that we need to keep the HPC approach, no compromise on performance. So this is not a very beautiful, but this is something which is quite powerful. This is a HPC storage appliance. So within it, it's InfiniBand. We have looked at all the PCI lane. We have calibrated the memory bandwidth available for the socket. It's a HPC system. So it's not something which work well for this specific workload. For example, just read. No, it's work well also for write. And this is important. And why this is important is that basically, originally, AI was a read-driven workload. It was about the ability to ingest a lot of data, feed the GPU, then we do the training, and then at the end of the training, we write the result back. So it was really read-driven. With this offloading techniques, it means that there is a back and forth data movement across the system. So we feed the GPU, but the GPU is moving away part of the model when it's not the odd parameters, and when you want to trade some specific slice of it. So again, we retrieve, I would say, much more balanced data movement that we are used to see in HPC, read and write. So somehow the difficulties today is to deploy an appliance, to deploy a system which is able to cope with the evolution of the AI. So these are some of the references that I've used in this talk. And if you have questions,